Hi, this is Ms. Bosque, and today we're going to talk about the polarity in covalent bonds. Covalent bonds share electrons, but sometimes electrons are not shared equally. As we can see here in this cartoon, in water, oxygen is going to try to pull more electrons than the hydrogen. So there's going to be a polarity here. So for this, you need to get your C1 notes, turn to page 8, and let's get started. Okay, so covalent bonds are formed by sharing electrons between the atoms, but not all of them are going to be the same. Sometimes the electrons are shared equally, like here, or if we go back, in this picture, chlorine gas, and the electrons are going to be shared equally between them. And sometimes the electrons are closer to the more electronegative element. For example, water here, oxygen is going to try to pull more electrons towards it from the hydrogens. So if we look at this picture here, we can see that the blue is more electronegative than the red. So one side of the molecule is going to be more negative, the other side is going to be more slightly positive. And as we can see here, this is another example with hydrogen chloride. Chlorine is going to be more electronegative than hydrogen, so it's going to pull more electrons. And this side is going to be slightly more negative. This side is going to be slightly more positive. Sometimes when we have nonpolar covalent, which is a covalent bond where the electrons are shared equally. And how can you tell if the electrons are shared equally or not? We're going to look at the electronegativity difference, and if this is 0.4 or less, then we're going to have a nonpolar covalent bond. Let's do an example of this. Bromine. Bromine is found here. So remember the make 7 including hydrogen. When they're by themselves, they form a gas. So bromine gas, Br2, is just Br with bromine. So the bond between them, we look at the electronegativity for bromine, which is 2.8 minus 2.8. So that's going to give us 0. So this is a nonpolar compound. Methane is CH4. In this case, hydrogen cannot be in the middle. Hydrogen can never be in the middle. So carbon is going to go here. I'm going to have my 4 hydrogens. So at the end, I'm going to have 4 carbon-hydrogen covalent bonds. Because they're all the same, I look for the electronegativity of carbon, which is 2.5, and the electronegativity of hydrogen, 2.1. So I'm going to subtract them, and the difference is 0.4, so it is non-polar. When do we have polar covalence? Well, when the difference between them is larger than 0.4. If we're looking at hydrogen fluoride, hydrogen is 2.1, fluorine is 4. Fluorine is the most electronegative element. So 4 minus 2.1 is 1.9. So this is going to be a polar covalent compound. So the bond is going to be a polar bond. Okay, to indicate the polarity of the bond, we're going to draw an arrow over the bond pointing to the element that is more electronegative. We know that fluorine is the most electronegative of all the elements, so we're just going to go draw an arrow going this way. Then we're going to assign charges. Fluorine is not going to be fully positive. Fluorine is not going to be fully negative, and hydrogen is not going to be fully positive. They're just going to be slightly positive and slightly negative. If they were to be fully positive and fully negative, then we were going to be talking about ions, but this is covalent bonds. So this symbol right here is delta, with a negative and delta positive to indicate slightly positive, slightly negative. Okay, let's practice. For water, H2O, so we have our molecule of water. Okay, so we have two bonds. The bond between the hydrogen and the oxygen, if we look at the periodic table here, oxygen is 3.5 minus 2.1. So we are going to have two polar bonds. It's larger than 0.4. So two polar bonds. How many bonds are nonpolar? 0. When we're drawing the structure, remember to point the arrows towards the most electronegative element, which in this case is oxygen, and to assign the slightly negative and the slightly positive signs. What are the total number of bonds in dicarbon hexachloride? Remember that when we draw this, we put the least electronegative atoms in the middle. In this case, if we compare them with the periodic table, carbon 2.5, chlorine 3, so carbon is going to go in the middle, and we have 2, and then our chlorines all around them. Okay, so we have 1, 2, 3, 4, 5, 6, 7 bonds. Out of these 7, the difference between carbon and chlorine is 0.5. So we have 6 polar bonds. Carbon is 2.5 minus 2.5, that's 0. So we have 1 nonpolar bond. And when you're drawing this, remember to show the arrows going towards the more electronegative elements. In this case, fluorine into a sign the partially negative symbol. And then we're going to be left with the partial positive one with carbon or carbons. Pause this and come back to check it. Okay, to draw this dicarbon tetrafluoride, we do the valence electrons. So we have 2 carbons, 2 times 4 valence electrons per carbon, plus 7 valence electrons for fluorine, but we have 4 of them. We add them up, we have 36. Now each bond counts as 2. 2, 4, 6, 8, 10. So I'm going to subtract 10. And I have 26 electrons that I can place with. We're going to start with the ones on the outside. And we have 24, so we have 2 left. These 2, I'm going to place them on this carbon. Now to check 2, 4, 6, 8, all the fluorines meet the octet rule. This carbon 2, 4, 6, 8 But this carbon right here, 2, 4, 6. We need 2 more. So this one right here is going to share these, the lone pair, and we make another bond, and now 2, 4, 6, 8, 2, 4, 6, 8, we need the octal group. Okay, so what is the total number of bonds or bond groups here? We have 1, 2, 3, 4. This we count as a group. We have 5. How many of them are polar? Fluorine is the most electronegative of them all, so 4. Carbon is 2.4. So this is going to be a polar bond, and we have 1, 2, 3, 4 of these. How many bonds are non-polar? 2.5 minus 2.5, that's 0, that's going to be 1. Whenever you're drawing this structure, remember to show the arrows going towards fluorine, the most electronegative, and assigning the partial positive for carbon and the partial negative for my fluorines. Now we know how to calculate if a bond is polar or non-polar. Even if you have a polar bond or polar bonds, the molecule may or may not cause the entire molecule to be polar. So polar molecule means that one entire end is partially positive and the other end is partially negative. Right here we have this end with a partial negative and this other end with partial positive. So this molecule is going to be polar. Whenever they share them equally, if they're symmetrically arranged, then they're going to cancel each other and this is going to be a non-polar compound. So some of the questions that you can ask yourself to determine if a molecule is polar or non-polar are the following. Number 1, is there only one bond in the particle, and is that bond polar? If so, then the molecule is polar. Number 2, are there several identical bonds around the central atom which are symmetrically arranged due to there being non-shared electrons on the central atom? If so, this molecule is non-polar. So if we look at this one, this is symmetrically arranged. They both have the same kind of bond, so it's going to cancel out and give a non-polar compound. Are there several different peripheral atoms around the central atom? If there are, then the molecule is going to be polar. If we look at this one, we have chlorine, hydrogen, hydrogen, chlorine. So these two are the same, but these are different. So this molecule is going to be polar, with one side being more negative, the other side being more positive. Are there any unshared pairs on a single central atom? If there are, then this is going to be a polar molecule. Here we can see that carbon and chlorine make a polar bond, and we have 4 of these. So we have 4, but they're all symmetrically arranged, so they're going to cancel each other, and this molecule is not polar. This one, carbon dioxide, we have 2 polar bonds, but they're symmetrically arranged, so this molecule is not going to be polar. Here we have 3 polar bonds, nitrogen and hydrogen, but we have the lone pairs on the central atom. So this molecule is going to be polar. If we look, this side is going to be more slightly negative. This side is going to be more slightly positive.